All right, welcome to my N-body gravity simulation demo. My name is Colin Sinclair, and let's go ahead and get started. So the first thing about this program is that you have to have it on your local machine here, as I do on mine, and you'll also want to make sure that all of the requirements are installed. Those are listed in the requirements.txt file, and one of the sneaky things here is that FFmpeg has to be installed. And this can kind of be a process, right? If on a Mac, you have to first install Homebrew if you haven't done that, and then use Homebrew to install FFmpeg. And it can kind of be a whole thing. And so in the future, I'd like to freeze all of this and make it a standalone app that people can run. But for now, it exists in its separate parts, and let's just go ahead and see what it does. So I'll start by showing what's inside of my directory right now. And primarily, there's no videos directory here. And this is just to kind of show off a nifty little organizational thing that this program does. So let's go ahead and run the program with the Python 3 main.py, and we'll go ahead and let it do the magic. So it says, welcome to Colin's N-body gravity simulation. Press return to continue. This program simulates the time evolution of various gravitational systems like the sun and moon, a planetesimal disk, or a star cluster. The simulation is based on the leapfrog method, which is a numerical method for solving the equations of motion of a system of particles. This is for any of those nerds out there that maybe want to get into some numerical simulations, such as myself, or numerical computation. Each system has parameters that you can change to modify the simulation, which include the total duration, the time step, the number of bodies, the scatter of starting velocities, and more. So it's a highly customizable simulation. Each time you run the simulation, the program will store the resulting video in a videos folder that was created in the same folder you ran this program in, and it tells you what that folder is. Right? And so now there's a videos folder here, and that's going to be nice later on. Okay, so we have this whole menu system. There's 9 different initial conditions for us to start with. Some of them are obvious, like the Sun-Earth system, the Sun-Earth-Moon system, a circumbinary planet system. Others, I've included a little bit of description. And so, for example, the figure 8, the description says, a 3-body initial conditions for a classic example of N-body choreography, the obscure art of finding perfectly periodic N-body solutions. So let's go ahead and start easy. We'll just start with a Sun-Earth system. So I'm going to press 1 and then enter. And it looks like we have some things to customize here. So we can do the duration and the time step. And there's a little description here that tells the user what these things are. And I've actually struggled to decide whether or not I wanted to keep the time step as a part of this whole experience, because the time step is really more a testament to the limitations of numerical computation and integration. It's not so much to do with the actual physics and the gravity and the space. So I've left it in here for now, but this could be something that I remove later on. Especially because as it stands, the whole program is designed specifically to pass 1 year in the simulation every 15 seconds outside of the simulation. And so changing the time step doesn't actually change the rate that time passes. It does make it more or less choppy. And of course, the physics gets less accurate with larger time steps, but it goes faster. So let's just start off by using some default values. I'll press a 1 here, and it's going to go ahead and calculate the trajectories and animate for us. Now, this step takes a long time. It's Python, it's using Matplotlib. Generally, it is just a slow thing to do. And so I've actually told it to print out some space facts every so often for the user, just to kind of keep them engaged as they do this. And then for the rest of this demo, I'm going to go ahead and actually just fast forward through these parts so that you don't have to sit here and watch this load every time. But we'll go ahead and let it load this first time. We have some space facts. We're starting off with the initial state of the universe, and then we're just going to kind of walk the user through what happened with the Big Bang and the early universe. Maybe teach some space enthusiasts some space facts. And we have this progress bar that's kind of showing us where we are. And you'll hear my Intel MacBook Pro starting to fan up as that processor gets nice and warm. Now, another thing I want to mention while we're just kind of waiting here is that initially this program, I wrote it as a final project for one of my classes a year or two ago. And at the time, it was really quite elementary. There was not much interesting stuff computationally going on. It wasn't interactive. There was no interface, and it was a terrible resource hog. And so it would actually calculate all of the trajectories for all the particles and then animate based off of those trajectories. And it was holding all of this information in memory. So what I've done now is combine that trajectory calculation and animation into one step. And now there's a lot less of a memory footprint, which is nice. So it's going to go ahead and open the video for you in your default video player. And before it even starts, you can see, hey, there's a sun, there's an Earth. These particles are scaled by mass, but there's a minimum and a maximum because on a computer screen, from this vantage point, you would not be able to see the Earth if the sun were this big. And so, and I didn't want to make it too much bigger because, we want to be able to see the orbits play out. So I did set some parameters here. Let's let it play here. And it's exactly as you would expect. So we have this isometric 3D view here where the particle gets kind of fainter as it's behind the sun. And then they swap places when the Earth passes in front. You also have this edge-on view and this face-on view. Finally, we have this graph up here of kinetic energy, and it's showing the kinetic energies of the particles. The issue with this is that this color should be this color. They're supposed to be the same, and they're based on the distances from the origin. That's a bug to fix in the future. I haven't gotten there. But anyways, they're perfectly stable, right? The sun is at the center, so its kinetic energy is 0. And the Earth is obviously moving very fast and has mass, and so its kinetic energy is up here, but they're not changing, and this is a very simple intro simulation. So, okay, there we go. And really quick, I guess I just want to show here, let me open my Finder here. We'll go into my, here we go, data viz. Come on, new n-body. All right, so look, there's that videos directory. It was created, and that video exists now. So the user gets to keep that. It's labeled with the system name and the date. Kind of nice. So let's go ahead and do another simulation. Oops, there we go. I'll say yes. All right, so let's go ahead and skip forward. There's a lot of options here, but I want to show the coolest ones. So let's check out this Planetesimal Disk. This one's really cool, and this tends to be people's favorite. So let's go ahead and run the Planetesimal Disk. And actually, let's do some customizing ourselves this time. So let's not use the defaults. I'm going to enter my own. Enter the duration in years. So let's do 3 years of integration. And time step in days, let's go ahead and do 0.5 is good. That's high enough resolution for it to be mostly accurate, but not crazy long. Number of particles, 30. That's kind of a lot. Let's take that down to 15. Speed up our animation a little bit. The mass ratio, here we go. So this one's kind of interesting. It says the evolution of the system depends on the ratio of the mass of each planetesimal to the mass of the central star. At very small values, the gravity is totally dominated by the central star. At larger values, above 1 times 10 to the minus 6, roughly an Earth mass per particle, the orbits may start to get unstable. Let's go ahead and let's have some fun. So I'm going to enter my own here. And I'm going to say, let's do a mass ratio of 0.001. Now let's do 1,000th. That's a little bit better. Okay, and then finally the z velocity, right? So up and down out of the plane. Let's go ahead and let's double it. It's pretty tame as it is. Let's just go ahead and double that z velocity distribution, and it's going to go ahead and work for us. And I'm going to, at this point, just fast forward to the point when it's done. All right, so we've just about finished up this animation. So here's our video. It's very exciting, and let's go ahead and watch. So at first we can see, hey, there's some planets. They're all kind of like lopsided on one half of the star. That seems kind of unlikely given that these are generated at random, but kind of fun. And then here we have our edge-on view, and you can see just how flat the system is at the first instant. And let's just go ahead and start and see what happens. Ooh, okay, lots of stuff to watch. So first, those initial z velocities have changed, right? They are no longer flat, the system. And you can see there's kinetic energies kind of everywhere. Now that central star, its kinetic energy is low. It's lower than everyone's else because it's moving slower. But it's very massive, and it's actually being pulled around a little bit by the planets. And remember, these planets are only 1,000 times less massive than the star, which sounds like a lot, but is actually a lot more than what we see in real life. At least for the rocky planets. And you can see there's a lot of interesting stuff going on with the kinetic energies here. Those outer planets, the ones furthest, have the most kinetic energy because they're orbiting faster. And then, the inner planets, the closer ones, have more kinetic energy because they're orbiting faster. The outer ones have slower kinetic energy, or lower kinetic energy because they're going slower. So there you go. That would be a nice thing to teach people. Slower kinetic energy. If you're going slower, you have lower kinetic energy. That kind of works. So there you go. Kind of an interesting demonstration of how these things play out. And you can see like there's certain interactions that are causing these planets to slow up and slow down and speed up and kind of going back and forth. So that's kind of cool. Anyways, let's go ahead and quit out of this. It's very neat. You can see, oh, look, the plane kind of leveled itself out back again to flat, right? If we go back, you can kind of see, well, actually, it never really got crazy out of whack. Yeah, you know what? That phenomenon's not super present here. If you have a lot of planets, it's actually quite cool to see the system start off very three-dimensional and then kind of collapse back down into 2 dimensions. But those simulations take a long time, and I have since cleaned my directories out to save space, and so I don't have them on hand. Something to look at. Oops, okay, I did the wrong thing there, but here we go. It's telling us my videos are stored here in N-body videos. That's nice, and they take up 2.3 megabytes total. Okay, so let's go ahead and do this one more time, and I want to just do the... oops, I can't. This, by the way, is designed to be a little bit more robust. I can't enter the wrong thing. It's going to say, nope, you need to do something. So let's do a tiny cluster. This is a tiny cluster of stars. And let's go ahead and say, I'm going to do my own. So we're going to do 1 year at 0.1. And this is because the tiny cluster is extremely susceptible to the issues with numerical integration. And so we'll do this. Number of particles, 20. That's fine. Maximum mass. Yeah, let's get some ejections going on here. So we can enter the maximum mass in solar masses. Let's do 3 solar masses. Okay, so we're going to get some serious interactions and collisions going on. And we're going to run this, and again, I'll just skip through all of this, and then we'll come back. All right, so this is just finished up after a lengthy 10 minutes of integration. And here it is. So we've got our star cluster here. Each of these is a star with a mass of no more than 3 times the mass of the sun. And let's just watch this go crazy. And actually, because of the time steps, QuickTime is actually thinking this is a slow motion video, which it isn't. So let's go ahead and do this. Oh, and already I'm actually seeing up here in the kinetic energy graph that we are not conserving energy. We're creating some, but let's go ahead and watch. All right, so, oh, and there they go. Oh, that's so sad. They actually dominate the system. That's upsetting here. So we've got these 2 stars, this pink one and this yellow one, and they must have flung around one another or maybe just other stars, and they went so far away so fast that we actually kind of lose all dynamics in the system. So there they go. Man, I wonder if we can, and what's really cool is that we can actually go ahead and slow motion this with QuickTime here. So let's see if we can see that happen. Ooh, we just missed it. I'm going to go back even further here. We don't need to watch them zoom out. Okay, let's see. Oh, yep, they flung right around each other right there, it looks like. Right in here. And there they go. So that's another thing, is that this algorithm could certainly use a facelift to favor conservation of energy rather than conservation. Well, it's not conserving anything right now. It's just using kinematics. But there you go. There's a little demo of this whole little program here. I hope you enjoyed it. Oh yeah, and I changed some parameters. So let's just go ahead and delete. It's only deleting the unchanged one. So we'll say no. We're at 3.3 megabytes. And thanks for using the simulation. So there is my N-body gravity simulation in all of its glory and its flaws. I hope you enjoyed. Thanks.